Thank you so much, Annette. It's a wonderful honor for me to be here on this inaugural meeting, and I am extremely grateful to the committee of the APS for its choice. For about 150 years, psychologists have dreamt of being able to decompose the series of operations that are going on in the brain of a person as a task is unfolding. This is the problem of decomposing a cognitive task. And it all started in this country with Franciscus Donders, who showed us that reaction time was not instantaneous and that it could be decomposed into a series of stages. And this was later pursued a century later by Saul Sternberg, who gave us the additive factors method. Then many other people in psychology contributed to this difficult methodological task of finding ways of decomposing the series of operations. Mike Posner, Roger Shepard, many others. What I would like to show you today is that new tools are available, and they are psychological tools. But because they look at brain activity in real time, either with EEG or with magnetoencephalography or both at the same time as we do in the lab, or sometimes with intracranial electrodes in epilepsy patients, they are able to look at the time course of brain activity and to let us know of the unfolding of information in time in the brain of a person. But as you know, data from these tools is extremely rich and complex to analyze. And what I would like to show you today is that there is a way to analyze it, which is exciting, which gives us more direct information about the time course of unfolding information in the brain. I will be using this tool in order to look at the unfolding activity when a subject is conscious of a certain piece of information, or where the information remains unconscious, and try to define what is the boundary between these two states of processing. So I'm going to talk about a technique called multivariate decoding, and it is a mathematical technique, but I'll try to make it very simple for you. And I'm sure many of you are already using it. What we can do is, if we have this time series of recordings from brain activity, such as we have, for instance, 304 channels of MEG and maybe 128 channels or 256 channels of EEG, we can essentially consider a slice of time, and during this slice of time, we think that these brain measures are giving us information about a certain stage of processing. What we can do is train a machine learning algorithm, support vector machine, to find where is this information. The algorithm will detect what combination of the sensors at this time is available to recover the information the subject is processing. For instance, if you flashed a vertical versus a horizontal grating to the subject, you can ask, when in my recording do I find information about a vertical versus horizontal grating, the orientation of the grating, and you will find this nice curve where before the stimulus there's no way to decode it, but at a certain point after the stimulus, suddenly you get above chance decoding level, and you can tell, therefore, that the information is being encoded in brain activity, and you can see it unfolding in time. Now, as you follow it in time, the decoder may change. It need not be the same hyperplane, the same decoder, which is separating your data, which can be used to separate your data. And therefore, one thing we can ask is, how stable is this information? Is the decoder at time t1 still able to decode the information at time t2? What I will be showing you is these matrices where we look at the training time when we train the decoder, but also at the decoding time we can try to see if this decoder generalizes to new data from another time. And these matrices of training by decoding time will tell us a lot about the unfolding mental representations. Let me give you an idea of what I mean by this. Imagine that you have a chain of successive operations, each processing the information, maybe through successive brain areas. Well, in this case, you should be able to train a decoder at a certain time, but it will not generalize to the other time, presumably because the representations are being displaced, different sensors are being engaged. If, however, there is a sustained activity, it will show a completely different signature. You can train at a given time, but you will be able to find the same information at another pattern, at another moment in time. So you should be able to decode chains of processing and to see a complete difference with sustained processing. You might even be able to see that there is a reactivation of processing. Maybe the same process comes up the second time and your decoder is able to show it because it is showing the information rises again. This is when you have a single task, but imagine now that you have two tasks. Then things begin to be really interesting. You can train your decoder on one condition, C, but you can test its generalization to the same condition or to another condition, C prime. So the matrices get a little bit more complicated. But if you think about what this means, imagine, for instance, that in one condition there is a fast chain of processing, and in another condition there is a slower chain of processing. Well, these temporal generalization matrices will show it directly, because instead of having the activation along the diagonal, you will see a shift away from this diagonal. I hope this is not too abstract, but I'll give you many examples in the next slides. So what you have on screen are different examples of what may occur during information processing. Maybe one condition branches to one process, another condition branches to another process. This again will have a specific signature of not generalizing across conditions. Maybe the processes go forward and then they reverse in time. Again, this will have a specific signature. So in all of these cases, we may have diagonal decoding for one task, but the generalization to a different task will show you very specifically what is happening. This is almost like a radiography of what's going on in a task. To explain it in a slightly different way, there was a time in reaction time in mental chronometry where we were worried that we were having offline tasks, that we were always having a response at the end of processing. But with these techniques now, we're really seeing everything in real time, and with this decoding technique, we can really ask, where is the information, how is it traveling through time in the space of the brain? But notice I'm not showing you brain images yet. We don't need to know exactly where this is occurring in the brain, but we can recover it in a sort of psychological space of the information which is being processed by the subject. So I immediately want to give you an example. I hope it will be familiar to you. This is the so-called mismatch negativity, P300, and a paradigm that we call the local global paradigm. Let me play the sounds for you. Okay, so you've just generated the brainwaves I'm going to analyze now. We should have recorded this room. So what you heard are a series of tones, and then there was a different one. And this is typical of the so-called mismatch negativity paradigm. You'll get a mismatch response from the brain to a novel tone, which is not expected after habituating to a series of repeated tones. What we do here is we repeat it several times. And when we do that, you habituate to the whole sequence. The whole sequence begins to be familiar. And then you noticed at the end, I gave you something different. I gave you a sequence where all 5 tones were identical. And the surprise here is that there was no surprise. The surprise is that the last tone was not different, whereas you expected it to be different. So there are 2 different forms of surprise here. There's a local surprise and a global surprise. We can then make them completely orthogonal by having a different block where subjects expect 5 identical tones, and then they are surprised by the sequence with a deviant tone. So I think you understand that this is a 2-by-2 paradigm where we can have local novelty, whether the last tone is different, and we can have global novelty, whether the whole sequence is expected or not. What's quite striking is that the brain generates very different responses to these 2 things. It generates a mismatch negativity to the individual tone here, even when it's completely expected. Even when you know that's what you're going to get, you still get this mismatch negativity. However, you don't get the P300 waveform here. You only get it when you have these rare deviants where the whole sequence is unexpected. In other words, this is a very brief summary of what we get in this paradigm, a complete separation between early events that react to the local novelty and reflect the local transition probabilities between sounds. And we can show, using various techniques such as fMRI or intracranial recordings or MEG, that this arises from the auditory cortex with an early latency. And the global effect is completely different when you have a conscious expectation of the whole sequence, violating the whole sequence, even if it is as banal as a monotonic pattern of 5 tones, will generate a more global response, extended in time, starting around 200, 300 milliseconds, and invading various areas of inferior frontal cortex, anterior cingulate, inferior parietal cortex, and so on. So 2 completely different networks. Well, why am I showing this? Because the decoding tells you much more directly than all of these brain reconstructions that something very different is going on in these 2 cases. We can train a decoder to either decode whether the last sound is different or whether it's the same, or we can train a decoder to tell whether the whole sequence is rare or whether the whole sequence is frequent. And these decoders are orthogonal to each other in this situation. They are independent of each other. You can see that as a function of time, the decoding gives you very different time courses for these 2 pieces of information. Fast rising pattern followed by decay in the case of the local effect, a much more slowly rising phenomenon sustained in time, really staying there for a long time for the global decoding. Why is this interesting? Well, because we can see that the information is not present in the brain at the same time for these 2 effects, because we can see that this can occur even when a subject is not responding at all. So we don't have to do mental chronometry. We can look at representations in the absence of an overt response. Also because this can improve the detection. We are training a decoder on single subject data. We are training the decoder on a single brain. Therefore, we don't have to average across subjects, or if we do, we average after we have done the decoding. In other words, we don't average as is usually done with ERPs or MEG recordings. We don't average the sensor data. We average after we have projected the data back into psychological space. We average after projecting the data into the novelty space, whether the sound is novel locally or globally. So by doing so, we take advantage of the high resolution of the recordings within a subject, but we also take advantage of the averaging after we've extracted the psychologically relevant information. Now, this is still just looking at how we can decode as a function of time, but how about these matrices? When we look at this generalization across time, we get this beautiful time course of information, even in such a simple paradigm. So just to explain again, so here we have training time on the y-axis, we have generalization time on the x-axis. So what this means is we are training a decoder with data from this time slice, and we are testing all of the other possible times. We are feeding it with data from all of the other possible times, and we're asking, can it generalize? Is there information? And we find, as you can see, that for this local effect, there is largely a diagonal pattern. Information is present for some amount of time. This is the black curve here and the yellow surface. There's a lot of information until about 400 milliseconds here, but it is local information in time, in that if you train a decoder here, this is the pink curve, it will only generalize for a short period. In fact, it will even reverse. You can do worse than chance, what that means is that the brain pattern reverses completely after a little while here. But you can see that the decoding can continue for a little while. Basically looks like a chain of successive processes. Why am I excited about this? Because the pattern can be completely different. If now we train the decoder on this global effect, whether the global sequence is different, we find that the pattern is one of highly sustained activity. As you can see, wherever we train the decoder, we basically can generalize to the other time points after it. There is a little bit of a diagonal pattern, but mostly it's a square pattern where information remains sustained over time. If you know that you are in a novel sequence, your brain flips into this state of knowing it for a long time, holding to the information. So what used to be very similar phenomena that are often associated according to sound novelty, MMN and P3, begin to be to look like very, very different phenomena. One that relates to a chain of processing, another that relates to stable processing. One of the reasons we are excited about this is that it relates to a dissociation of consciousness. We know for a long time that the mismatch negativity can be preserved even when you're not conscious, can be preserved in particular if you are in coma or if you are anesthetized. And many people have thought that the P300, on the other hand, reflects the ability to gain an awareness of the novelty of a sound or a sequence of sounds. Well, we've been pursuing this very much, and I will just skip over this because this is more medical than psychological, but with Lionel Nakache in the Salpêtrière Hospital, we have been able to show indeed that this dissociation between mismatch responses and P300 responses maps onto a distinction between unconscious and conscious processing. And so the mismatch negativity is not a good marker of consciousness in these patients, but the P300 waveform, if it is present, the global response, if we can decode it, is an interesting marker that suggests that the patient currently is conscious. And as you know, this is a difficult problem because some of these patients after massive lesions or car accidents may not be responsive, but yet still be conscious inside, not be able to show that they are conscious. So with this test, we believe that we can help to detect whether a person is or is not conscious. I don't want to say that this is a unique marker, and many of us are working towards different sorts of markers of conscious experience. If the information is stable in time, it is very likely that the brain is talking to itself, and there are reverberating loops that are maintaining the information. And we also found that indices of long-distance communication across a significant time period are extremely helpful in separating the patients that are conscious or minimally conscious from those that are vegetative and who are thought not to be conscious. Well, where is this leading? I think we begin to have a theory of what aspects of processing are unconscious and what aspects of processing are conscious. This is ongoing work. There are many labs working in this domain, but I am trying to synthesize many observations in the framework of this global neuronal workspace hypothesis. So let me tell you about it for a second. It is very simple. We all know that in psychology, there are many processes that can unfold unconsciously. In the brain, there are many modules, local circuits that can operate without consciousness. And this can be depicted very schematically as all of these little circles that are chained together. There can be chains of processing without consciousness. So what corresponds to consciousness? Well, according to this idea here, consciousness relates to a second system. A system that is there to break the modularity, to make systems talk to each other, to take information from one system, make it available to the others. So this is symbolized by this set of central systems here that each have a different piece of information, but now are able to broadcast it to others extremely broadly, share the information, make it stable enough that it can be held in working memory and therefore passed on to other processes flexibly. So the claim here is very simple, is what we experience as consciousness is in fact the global availability of information. If we can report it, it's because the information has been extracted from whichever module it was in and has been made available in particular to speech production systems that are able therefore to describe what is the content of this information. But we can also describe it not just to others, but also to us. We have the information internally, we can route it to whichever processor is needed for a given task. There is a neuronal component to this theory. The idea is that there are specific types of neurons, pyramidal neurons with long-distance axons that are needed to share the information and dispatch it to other processes. And there is also a claim about the dynamics of this system. The idea is that because this is a highly interconnected system, it can operate in two modes. There is an ignition mode. If there is enough information, the information will begin to reverberate, self-amplify, and gain access to this workspace system. And this is what we call the ignition phenomenon. It is what makes the information stable. A piece of information is stabilized by these reverberating loops and becomes metastable for the duration of a task. So this is a very short view of this theory, but just a very simple aspect of this theory is that it shows that there are at least two ways to make information unconscious, to interfere with conscious access. One is that you can reduce the incoming activation. And the claim is that this is what we call subliminal. If we mask a stimulus, for instance, we will prevent its activation from reaching the threshold value which is needed to ignite this central system. There is another way, however, which is what we call preconscious. If we distract the subject, if we make it such that there is already one object, one piece of information which is in this workspace system, then a second piece of information, even if it is climbing through a series of stages and reaching this central stage, may not be able to enter because the system is already occupied elsewhere. So this would correspond to inattention or attentional blink, for instance. So I'm going to tell you about experiments that cover these two different domains, and I would like to show you that we can use decoding and brain imaging to track very precisely in time what is happening during these situations. So let me first tell you about a few experiments on masking. Masking is a wonderful phenomenon to make things invisible. I can take a digit or a letter and I can make you blind to it. I'm going to try to do this right now. Several people have seen this demonstration. We'll see if it works. This is good old E prime, which we are no longer using now, but let's see if this works. So you have a fixation dot here. Please keep your eyes on it. And then on the side, I will flash a digit. It should be just for one frame of the projector, hopefully 16 milliseconds. Then there will be a blank, and we will vary the duration of that blank. And then there will be letters, and the letters will serve as a mask. Notice that they are surrounding the digit, okay? So you're ready? So we start with a long duration. And I hope you can see the digit. It should be there all the time. 9. Okay. We make the delay shorter, and the digit is still highly visible. In fact, it's equally visible. Now we make it a bit shorter, and maybe on some trials you might not see it. But now if we make the duration 33 milliseconds, I hope that the digit is no longer visible. I know this projector is not great. There is a splitter on screen, but hopefully on most trials, the digit should be completely invisible. Is this working? Okay. All right. Okay. Yeah. It keeps. I think the projector here is doing a trick. It's not exactly having synchronized frames, but by and large, this is the experimental situation in the lab. If we are below a threshold, it looks like there is no digit at all. Yet the digit is there. It's on your retina. It's being flashed. So the question is, how far does it go, and why is it not visible? Well, so these are the different delays we've been using from 16 milliseconds to 100 milliseconds, and the threshold value is around 50 milliseconds here. But in every trial, we ask subjects, did you see it or not? We ask them to report their consciousness. And the predictions from the global workspace model are quite simple. There should be a progression of information. It's always the same information, the same digit, reaching your early visual areas, but it should be progressing and is being killed by the mask at different delays. So we expect accumulation of evidence and a linear accumulation of evidence being cut by the mask. But we also expect that there should be a threshold value where there is this sudden ignition, late stage ignition of a more global system involving prefrontal, parietal cortices, anterior cingulate, and this should create this late non-linearity in the system, where the values which are below threshold return to 0, but the values that are above threshold jump to a very high level. So linear followed by non-linear stages. And basically that's exactly what we found. In several different experiments, first with EEG, now with MEG, we systematically find that there is such a dissociation in the stages of processing. The early activation is linear. The green curve is the 33 millisecond condition that you just experienced. There can be some very high activation in visual cortex, in inferotemporal cortex, in fact, is in most of the temporal cortex, by an unconscious digit. There can be also activation of the parietal cortex for quantity to this unconscious digit. But notice now there is a second wave, and this second wave is particularly intense in the prefrontal cortex. And now the curves, if you look carefully, are highly nonlinear, and they map nicely with the perception of the subject. So they return to 0 when the digit is not perceived. Interestingly, this test is so simple that we can run it in babies. So Sid Quider, Ghislaine Dehaene-Lambert, my wife, and myself, we did this experiment where the digit was replaced by a face so that it was baby appropriate. And there were masks before and after the face, and we varied the duration of the face. And if you neglect the differences in sign and so on, which may depend on the different electrodes that we are using, but you can see that there are linear stages, completely beautifully arrayed activations here that are linear as a function of the face duration, and then there's a completely non-linear phase here, where essentially all of the short durations of the phase return to zero, and the brain waves are sustained only for much longer durations of the phase. It turns out that this threshold here separating these curves corresponds to the behavioral threshold for babies to orient to the faces. So we believe this is a real sort of phase transition, ignition, that seems to suggest that already in 5-month-olds and in 12-month-old babies where this was done, there is already a similar organization with linear accumulation of evidence followed by ignition. Now, what happens when I use my temporal generalization technique? Well, we get these beautiful matrices again. And so once again, this is training time, testing time. Now we have the shortest duration. Maybe the most interesting is a 33 millisecond duration here, where most of the trials are completely unconscious. And you can see that we can decode the presence or the absence of a stimulus on screen, even though you can't. You as a subject, you don't know that there was a digit. The brain knows, the brain is submitted to a whole series of activations, and we can decode them. But you see that they have mostly this diagonal pattern. The information dissipates along a sort of programmed pathway. The information goes through the system. But very different when we get above the threshold here. And even if we take the threshold data and we separate it into unseen versus seen data, you can see that we get a much more square pattern late in time, after slightly more intense activation initially, when the information has been reported as conscious on the part of the subject. When the subject sees the digit, the information is amplified, and the second stage becomes much more stable in time. The information is stabilized. This notion of metastability as a correlate of conscious perception has been pursued also in several papers by Aaron Scourger, now in the lab, and there is a paper in PNES in press with another measure of stability showing that it also works in many other conditions, such as color fusion invisibility, for instance. Now, we can go further than that. Here we were just decoding whether the digit was present or absent. Now that can be criticized. When we just contrast seen versus unseen trials, some of these differences could be due to a lot of factors that have nothing to do with consciousness. Maybe you're surprised, maybe you are more attentive when you see something, but maybe these are not, strictly speaking, conscious processes. So here we have a slightly different strategy. We are trying to inject highly specific information inside the brain, and we are going to try to track this information through time and see how the coding of this information differs on conscious and unconscious trial. So the information that we are injecting in this new experiment is the location of a bar, can be at one of 8 locations. We mask it with a masking pattern. We're going to ask, can we decode that location, and does the code differ on conscious and unconscious trials? Now, there's another problem with most experiments on consciousness, is that the late activation that I'm showing you could reflect the much higher performance on conscious trials. When you're conscious of a piece of information, you typically perform much better. There are lots of things that you can do. It's a natural consequence of becoming conscious of a piece of information. But in some cases, we can use an interesting phenomenon called blindsight, where there is, in fact, behavioral reaction, accurate behavioral reaction to a stimulus. So in this condition where the location of the stimulus is the cue here, we can have not only physically identical stimuli that are sorted into seen and unseen trials, but we can even have physically identical responses. The subject is responding way above chance to the stimulus. So physically identical stimuli, physically identical responses, but yet some seen and some unseen trials. So here's the paradigm. We flash a target for 33 milliseconds, we mask it. The subject immediately tries to report its localization, so we have this high blindsight condition, and then later, just a little bit later, the subject reports whether this was a seen or this was an unseen trial, according to him. It's purely subjective report. What you can see here is the behavioral performance. Of course, on seen trials, subjects are quite good, but even on unseen trials, they are way above chance. Even though they say, you know, there was no stimulus, I couldn't see it, they very often click at the appropriate 1 out of 8 locations. And so we can select those unseen correct trials as our blindside trials. Now, what can we decode? Can we decode the location of a trial? Well, chance would be 12.5%. We can do better than chance as a function of time. As you can see, we see the information rising and having this two-peak pattern here. If we pick the information at these different times, you can see these decoding matrices. There are 8 possible locations. There are 8 real locations. There are 8 decoded locations. You see this diagonal pattern indicates that we are doing really quite well in telling on a single trial basis without averaging where was the target. It's way above chance. And we also see the information evolving. It's a little bit imprecise here. It gets really precise here. Now, the question is, what do we get for seen versus unseen trials? So this is a slightly different way of showing the information as a function of the distance between the real and the decoded location. And these are the same curves as a function of time, sorted into seen correct, unseen correct, and unseen incorrect trials. And you immediately see that there is a difference in decoding, especially in the late part. The initial peak is essentially identical, but the late part, starting at 250 milliseconds or something like that, is essentially super amplified on trials where there was visibility on the part of the subject. You can also see that there is more information decodable from the brain when the subject is able to react appropriately on these blindside trials, even if it is unseen, compared to trials that are unseen incorrect, where the subject does not report seeing and is also making an error in responding to the location of the stimulus. So there is clearly amplification of information and 2 steps, one for blind sight, but even more information when it is conscious. And we can ask, about generalization in this situation. So imagine that we train our decoder. Now we just train it to tell whether the location was left or right, just to have a binary response. But we can train it on the unconscious trials, and we can see whether it will generalize to the conscious trials. When we do that, we find essentially identical generalization. That is to say, there is just as much information on the subliminal, the information that we extract from the subliminal trials is essentially equally present on the conscious trials. It looks as if there are a number of processes that contain decodable information that continue to have this content even under the conscious condition. However, we get an asymmetrical pattern of generalization when we do the converse. So if we train the decoder on the conscious trials, the decoder is able to find more information that is not present on the unconscious trials. So the suggestion is that there are additional brain regions that are unique to conscious experience that have been extracted by the decoder. There is more information. It's been amplified. Where is the source of this amplification? Now we can go back to brain images. We can try to reconstruct the sources of the brain activation. As you know, this is not a perfect exercise. The data does not allow you to unambiguously go back to brain activity, but we can have gross regions of interest, and I've plotted 3 here, the calcarine regions, the superior parietal cortex and superior frontal cortex, and in each case we can retrain our decoder just on the sources within these areas, or a subset of sources. And what you can see is that this amplification pattern is a little bit present in the calcarine cortex, but mostly it is present later on. You can see the temporal unfolding of these patterns. It is present later on in superior parietal and superior frontal cortices. So the suggestion is that once again, this global workspace system is having more information. The information has reached a new level of information coding on conscious trials compared to unconscious trials. How about my matrices of temporal generalization? Once again, they are very, very telling about the time course of information. So these are again these matrices where we train at one time t, we test at another time t prime, we do that for all combinations of times, and what we find is there is a transient effect and then there is a more stable effect. Okay. But I'm going to look at this more closely because it's a little bit weird. In order to see it more closely, I'm going to transpose these matrices. These are exactly the same matrices, but not really transpose. I'm going to rotate them just slightly so that now what we see is on the y-axis the temporal distance of generalization. how much forward or how much backward can we generalize when we have trained a decoder on a certain training time here, okay? So let's look at this. Basically, we have a first decoding point here. Quite early, we begin to be able to decode the location of the target. This presumably corresponds to the activation of retinotopic areas early on in the visual system. And this is the same for seen and unseen. One difference, though, is that if you've trained a decoder here, you can decode the same information a little bit later with a pattern of reactivation suggesting top-down inputs into the visual cortex on seen trials more than on unseen trials. But what's more interesting is then we have this subsequent, well, we have clearly a sort of chain of decoding here, and then we have this very different event, sort of explosion of information in the system here. And you can see that at this point, we begin to get better decoding on the unconscious, on the conscious, sorry, compared to the unconscious trials. But something very weird is happening here. The generalization seems to be longer on non-conscious trials compared to conscious trials. And when we first saw this, we were really puzzled. You know, usually, the thought from priming studies, for instance, is that unconscious information dissipates quicker. And this is a case where it seems that information that is unconscious does not dissipate as fast as when it is unconscious. So what's going on here? Well, it depends a little bit how you look at this. If you look at it horizontally, there is more information on the conscious trial. It lasts longer. There's a plume here that really lasts for a long time. But here, it's the vertical generalization. Essentially, there is a sort of square pattern that dissipates over time. So we think we can understand this pattern by looking at the horizon of generalization. During conscious processing, if you find a good decoder, the pattern here suggests that you can continue to decode for about 160 milliseconds forward. And then it changes. The pattern keeps changes. And maybe this has to do with the task the subject is doing, this complex task of reporting one of 8 locations, so programming the hands, the fingers, and so on. The information must be traveling through the appropriate motor program. There's generalization in a backward direction. Now, in the case of the non-conscious processing, we have, on the other hand, this sort of single duration for a single process that generalizes over time. So here is a quick picture to help you understand this pattern. On the left, the suggestion is that there is a series of stages because we have multiple decoders that don't generalize. So it looks as if the information is metastable for a period of 160 milliseconds, but then it's being translated into different codes because it is conscious. You don't seem to be able to do that when it is unconscious, and what you have is what we call failed ignition. This occurred in several simulations of neural networks that we've performed for this global neuronal workspace model. The information does not quite make it into the ignited state, and then it decays. It's basically a single state of representation. That's why it generalizes over time, but it also decays over time. So this is perhaps the best picture we have of conscious processing so far. Conscious processing is processing where the information is amplified. Because it is amplified, it is reaching this routing system where the information can be held, but also translated into a series of stages. This is what we call serial, effortful processing. Mike Posner and Treisman have given us these names many years ago. So serial, effortful, conscious processing, which is possible when you cross this threshold for consciousness on the left, but just decay on the right of the same information. Now, in the last part of my talk, I want to go back to this idea that there are multiple ways to make the information unconscious. And I've just told you about the masking paradigm, where we can make the information subliminal. Whatever effort you're making, even after, days or years of training with these masking stimuli, you still cannot see these masked digits because their strength is not sufficient, is being killed, it's not able to create this ignition. Now, according to the model, there should be this other condition where the information can be very strong, it's above threshold, but because the workspace system is occupied by another object, your attention is elsewhere processing another task, the information should be blocked. And we should be able to see this blocking, and it should be accompanied by a lack of consciousness. So, of course, I think we are very familiar with such conditions. We all know about the invisible gorilla. We all know about the attentional blink. These are exactly such situations where we're being distracted and we're not able to gain awareness of even something which is way above threshold. The minute we reorient our attention, the very same information can become conscious. According to this model, it's because it's gaining access to this workspace system. So, According to this model, there should be a very interesting relation between two phenomena that have been intensely studied in psychology: the psychological refractory period on the one hand, and the attentional blink. As you can see here, it's very clear. If the information is waiting for this second stimulus, it's being blocked from assessing the global workspace, what could happen? Well, two things could happen. It could just decay, and it would essentially become similar to the subliminal stimulus. You cannot recover it. It's gone. And this would be a plausible model of the attentional blink. Or it might be able to stay. Maybe it's in a buffer. Maybe it's not decaying very fast. You are able to turn towards it after you're finished with your first stimulus. You turn to it. You're able to gain consciousness of it. And according to the model, this would be a correct view of the psychological refractory period. What would happen then is that you would be delayed in processing the second stimulus. You would gain awareness of it late, but you would eventually gain awareness of it and be able to process it. So if this model is correct, these two phenomena are intimately related, and we should even be able to get them on the very same experiment. One trial may be the blink, another trial may be the PRP. So that's exactly what we looked for, and I'm just going to give you the predictions again very quickly. So we might expect from this model that the first stimulus, T1, the one that makes it into the workspace in the first place, would create this series of activation followed by this ignition pattern without being affected by the presence of T2. But the second target, T2, if it is presented just a little after T1, would still be processed by this initial chain of non-conscious processes, but then it would have to wait, and you would have a delayed ignition, or it would decay, and you would have a complete collapse, no global ignition, and this might correspond to the attentional blink. So these are the predictions from this very simple model. Now, here's the experiment that Sébastien Marty did in the lab, among several other experiments. We selected a sound as the T1, so the primary task, the first task for the subject is to respond to the pitch of the tone when it appears. You have to click one of two buttons to decide whether it's high pitch or low pitch. But at the same time, you have a whole stream of letters which is going on, and amongst these letters, you have to detect whether there's a Y or a Z. Okay, you have targets that may appear at any time, and they are non-targets, and you have to detect these targets. The targets always come after the tone, but they may come just after the tone. We vary the lag between the tone and the letter. It can be lag 1, lag 2, lag 4, or lag 9. Okay, so this is a clearly PRP-like situation. You have to respond as fast as you can to both stimuli, but there is one that comes first, and there is another that comes second. Well, the first thing I want to show you is psychological. It's just the behavioral reports from the subject, the behavior of the subjects. We are showing very clearly that both phenomena can occur on alternate trials, even with the same exact physical display. So there are a number of trials where you get T1 responses and you also get T2 responses, and the reaction times clearly show you this psychological refractory period effect. For those of you who are not familiar with this effect, the signature is that you get essentially constant responses to the task 1 regardless of the lag between T1 and T2, between the two targets, but you get extremely slowed responses to T2 when the two items get close together. So when T2 is very close, it's only just after T1, you really get this enormous slowing, and then it's only at long lags that you get normal responding to T2. But this is the reaction time. It's just the psychological refractory period. But on the very same trials, alternatively, we also got the attentional blink. So what I just show you is the trials in blue, where the subject was responding correctly to T2, given that he was also responding correctly to T1. But notice there is this huge number of trials in red where the subject simply did not respond to T2, did not detect that there was a target and that therefore he should click the button. And these are really blink trials. The subjects believed that there was no target letter. Okay. And notice that they do have this pattern of the blink, that is to say, they are not seen, all the more so that they are close to the target T1. So when there is a collision between the first target and the second target, you get these blink trials. So we'll be able now to analyze these using MEG, and I just wanted to give you an idea of how good these machines are. I don't know how many of you are familiar with modern MEG machines, but the signal that you get out of these machines is really fantastic. And so you can see, even with very basic Suss reconstruction here, that you can extract signals that reflect the moment where the tone was presented. You also get signals that reflect every single letter that the subject has been seeing from visual cortex, and you also get signals that reflect the motor cortex activation, for instance, of the button that the subject is clicking. Just 3 examples to show you that we really have access and separable access to different representations here. So now, how about decoding? These matrices are becoming familiar to you now, but I'm going to show the full power of these matrices now. So here we are. We train our decoder on the full time course of the first task that the subject is doing. How do we do this? We select trials where the subject responded to the sound, and we compare them to trials where the subject just listened passively to the sound without having to do a task. So the decoder is picking up the whole series of processes that allow subject to decide whether the pitch was high or low for the sounds. We train the decoder at lag 9, and we can see this whole series of processes, this familiar diagonal pattern now. Okay, starting with a narrow diagonal and then getting broader here. But then we take these decoders and we generalize to the other lags. And what you can see is that by and large we generalize almost perfectly. So whatever was ongoing at a certain time slice in this lag 9 condition still is going on in the lag 4, lag 2, lag 1, or even in the trials where the T2 was unseen. If you pay attention, you might see that we stay on the diagonal, but we get slightly off diagonal. I'll come back to that. There is a slight acceleration of the processing, which leads to this up diagonal pattern of generalization here. What about task 2? Task 2 is completely different. Again, we train the decoder on the whole processing of task 2. We do that by training the decoder to sort out trials where there was a target letter compared to trials where there was just a distractor letter. So we train the decoder once again on the lag 9, where we see this beautiful pattern of unfolding activity over time, and then we generalize. And as you can see is that when we get into the collision moment, we lose the diagonal. We go off diagonal, and this is in the opposite direction as here, is going towards slower processing. The processing seems to be suddenly slower, such that if you train your decoder, let's say at 300 or 400 milliseconds, you find the same information again, but later in time. It's no longer on the diagonal. What that means is that there is a process. You can find that this process is being repeated on these other trials, but it's being shifted in time. Notice how nearly empty the matrix looks like on the blink trials. These are the unseen T2 trials. There's a little bit of processing here that we can detect, and then it completely stops. And these are the same trials, lag 1 and unseen trials. They are the same physical trials, but sometimes the subject does not see the target, sometimes he sees it. That creates a huge difference. So I'm going to zoom in a little bit to show you that we can detect very fine patterns. So first we can do a reconstruction of the activation. So it starts in the auditory cortex, a little bit fuzzy reconstruction here. It moves to secondary auditory places, to the parietal cortex, and we see a little bit of the precentral activation that relates to the response. We can take a slice of time. We don't have to look at these complex brain patterns. We can just take a slice of time and ask, if we train a decoder at 200 milliseconds, how does it generalize over time? Okay? And how does it generalize to the other conditions of lag 1, 2, 3, 9, and the unseen condition? By and large, there is nothing to see here. What you see is that the time course of the first task is essentially unchanged, regardless of whether there is or there is not a second target just following. So the early stages are completely unaffected. The late stages are a little bit changed. So if you notice carefully, the onset is the same, and this might explain why the reaction time is the same. There is no change in reaction time to this first task, but the offset is slightly shortened when there is a waiting T2 stimulus. There is no such shortening, by the way, on the blink trials. Why? Because the subject is not doing the T2 task, so there is no reason to push the first task. It seems that there is pushing of the first task only when the subject is actually processing the second task. Now let me show you how different this pattern is for the task 2. So now, same exact picture, we're decoding a visual stimulus. It's detected as a target in the visual cortex here. It's being processed by the same sort of parietal areas for decision making, also prefrontal cortex, and leading to a response. So for each of these time slices, we can ask what's happening. We can see that the early stages are completely or almost completely unaffected. That is to say, even when a few hundreds of milliseconds later you're going to say, there was no target, I'm not responding, I didn't see anything, the brain is initially detecting, registering that there is a target. It's treating Y and Z differently from the other letters. By about 300 milliseconds, we begin to see big differences here. On blink trials, notice that there is a little blip of activation here, and then essentially it goes back to 0, and everything else is essentially not distinguishable from 0. So a blink trial is a trial where activation started and then it failed. Okay. On PRP trial, on the other hand, when the subject is eventually going to respond to the target, what we see is a dilution, a diffusion of the activation. The onset is similar, but instead of having this very sharp activation peak at this stage at 400 milliseconds, we have a progressive dilution of the activation, which lasts longer, ramps shorter, ramps with a shallower slope as a function of the presence of the T1 stimulus very close to it. So it looks as if this is something that can operate partially in parallel with the T1 task, but not fully, and creating interference with the T1 task. And finally, if you look at the late stages, they are essentially rigidly shifted over time. They are all shifted towards later times. There is a little bit of dilution as well, but this could be due to the fact that the reaction time to the first task is not absolutely constant. So there is variation in the duration with which the global workspace is being occupied. So we get essentially a sort of radiography of the psychological refractory period. And I'm excited by this slide because in one slide we're able to summarize the unfolding of two independent tasks and how they collide with each other. It's like, one of these CERN experiments where particles collide together. Here, two psychological tasks collide together. So when they are separated by enough time, we see them unfolding. The blue is the first task, the red is the second task. The area is showing when there is significant decoding. And so we can see the two tasks unfolding along their diagonals. That's by definition, because this is when we trained the decoder. Then we see what happens in the other lags. We see, first of all, this repulsive effect that I was telling you about. The first task is being slightly accelerated. The second task is being delayed. And the more we go into these shorter lags, the more this collision effect arises, the more we leave the diagonal for the red task. We can see that the beginning is still pretty much on the diagonal here. So these are processes that unfold essentially unaffected, but then there is this sudden delay, and we can exactly time when the information is being delayed here. We can tell now the brain is having a problem with the processing of the second task. Before that it was going fine, but suddenly there's a problem and the second information has to wait. I want to conclude with psychology, with current models of the PRPs and the attentional blink. There are several well-known models. I'm only going to discuss the basic models. There is one model which has been proposed by Hal Pashler, the central bottleneck, where the idea is very simple, is that you have a central stage which can only process one item at a time. It's very similar to what I just said. And so if the target 1 gets in, then target 2 has to wait. There's another model which has been proposed by Tombu and Jolicoeur, which has been called central sharing capacity, where the idea is that there is a bottleneck, but it's possible to split the resources for one task and for another task at the same time. So, of course, both will be slowed in this situation. Well, the data that I'm showing you is incompatible with both models, actually, and it's calling for a refinement of these models of the central bottleneck. Why is that? Well, first of all, as we saw, T1 processing is almost unaffected by T2, so this is essentially not compatible with capacity sharing. In fact, T1 processing is even shortened. This is incompatible with both models. None of the models predicted this, but it's compatible with the notion of lateral inhibition, where the fact that there is a waiting T2 shortens the processing of the T1 task. Finally, T2 processing is not just rigidly delayed. According to Pashler, it should just have been rigidly delayed, but that's not what we see. What we see is a little bit of parallel accumulation of evidence. Also, we don't see just a single stage. We see a cascade of stages that repulse each other from the T1 task and from the T2 task, suggesting that there's a whole chain. This notion of cascade that we owe to J. McClelland, I think, is very true here. And each of these stages seem to repulse each other according to the T1 to T2 task. So we are gaining, I think, a much better radiography of what's going on in these tasks. I just want to say that this notion of processing being suppressed, delayed, and diffused by dual tasking is essentially the same exact conclusion that was reached on the basis of behavioral paradigms by Ed Vull with Nancy Kanwisher. What they did was they asked subjects to report whichever letter was inside a circle. Subjects were able to do that quite accurately for the first letter, but then when there was a second letter that came just after, you could see this beautiful pattern of not reporting accurately the letter if it came in the lags between 2 and 5, approximately after the first one, and instead there was this dilution effect where the subjects were reporting the letter that was just before, just after. They were avoiding actively this period. So both dilutions, and also if you look carefully, you will see a delay where we tend to report the letters that come later, are completely compatible with this pattern of brain activation that we are seeing. Finally, I want to mention that there is a tight relation to consciousness here. People obviously have noticed that in the attentional blink there is a consciousness problem. We miss a stimulus that should be perfectly visible, but we miss it, just like the invisible gorilla. But in the PRP, is there also a problem with consciousness? Well, according to my idea, there should be a huge problem with consciousness in the PRP. It's not just that T2 is waiting, it's that T2 is strictly unconscious. And you only gain consciousness, according to the model, of T2 when you are finished with processing of T1. So this makes a very specific prediction. During the PRP, subjects should be blind to the fact that T2 is waiting. They should not know when T2 appeared. They should only gain awareness of T2 when they are finished with T1. So once again, we did one of these classical task. We always do it cross-modal, and it works very nicely even when it's cross-modal here. So T1 is a sound, T2 is a letter. There's a single letter here, so we make it very simple for the subject. There's only a PRP phenomena. They don't miss it, but they are quite delayed in processing the second letter as a function of the delay between T1 and T2. What we do here is we ask about their introspection. And part of the message of my talk, I'm sure you've noticed, is we can trust subjective reports. They are extremely useful in this situation. We can sort trials according to subjective reports, such as seen or unseen. This makes a huge difference when we look at the brain, and therefore the subjects are reporting something very real here. So in this extreme experiment, what we did here, every trial of this task, after the subject clicked to the first stimulus and clicked to the second stimulus, giving us objective RT1 and RT2 reaction times, we also asked them for subjective measures. We asked them to rate how quick were they in the first task? How quick were they in the second task? What did they think was the delay between the sound and the letter? Could they estimate it? And also, what was the delay between the letter and the end of their auditory decision, the first task? Okay. We train subjects to use scales to report subjectively subjective durations. So we trained them with the duration of tones, and then they had to use these scales to clearly report a reaction time. So it's quite an interesting method here to have the objective reaction time, and on every single trial we also have the subjective reaction time and all of these subjective duration measures. Well, it is late. I'm not going to go through the whole pattern. I'm just going to show you this reconstruction of what was happening in reality on the left and in subjectivity on the right. In reality, there is a huge PRP phenomenon. So this is the reaction time to the first task, and all of these bars here are the reaction time to the second task as a function of when T2 was presented. When T2 was simultaneous, the reaction time was very slow. When T2 was a bit later, it was a bit less slow, and so on and so forth. So you can see essentially the pushing of this second response by the presence of the first task, okay? But now look at the reconstruction from the subjective responses. Subjects were able to report on the RT1. In fact, there is a beautiful correlation on a single trial basis between subjective and objective reaction times. So on a single trial basis, your subjects know that they've been slow or that they have been fast. But what they do not know is that they were slower for T2. They are not aware of the PRP phenomenon. Although it's a huge phenomenon, several hundreds of milliseconds, they think that they responded equally fast to all of these trials. They're not aware that the blue bar should have been much longer. The reaction time was much longer when there was a collision. And furthermore, they are also wrong about the onset of the T2. If we ask them when was T2 relative to the initial sound, they are not aware of simultaneity, and essentially they report, this is the red bar here, they report T2 as occurring after they are finished with the T1 task. Okay. And they are correct about when the T1 task was ended, but they are not correct about when T2 was presented. They essentially have this huge blind spot. That's what we call the blind spot of consciousness here. They are completely unaware of what's waiting. They are unaware of the fact that T2 has been waiting when they are focused for a few hundreds of milliseconds on the processing of the first task, T1. Okay. So this is completely compatible with the story we get from brain imaging. The global workspace being occupied, you are not able even to know when a second stimulus is being presented. But as soon as the global workspace is free, you can turn to this second stimulus and then you gain awareness of it. I'm aware that I presented you a lot of data, but I think first and foremost, I want you to remember the methodology. It's possible now to supplement reaction times with measurements of brain activity, and it's possible to follow this brain activity over time, to decode it. So it's possible to largely ignore where this activation is occurring, but to return to the stimulus space and ask what was the identity of the stimulus. Where was it on screen? Did the subject register that it was a digit or not? And so on and so forth. I think this is a highly sensitive method to probe the time course of information processing, much better than just having a single reaction time at the end of the trial. There is code available, and people have become very good at sharing code now for processing of this MEG data. So I invite you to look at this M&E Python suite, which is completely free and open source. Now, in terms of psychology, my main conclusion will be that there is a long time before we are conscious. The initial stages of stimulus-evoked brain activity reflect non-conscious processing, and this can be as long as 300, 400 milliseconds, depending on the experiment. Conscious perception seems to relate to a late period where information is amplified, becomes metastable, and can be entered into a slow, sequential series of processing stages associated with the ignition of distributed parietal and prefrontal networks. I think this talk also raises several interesting open questions. I will just mention them. The first is, it's still very difficult. Can we purify consciousness research? Can we find a pure moment where we isolate the moment where the information enters into consciousness? As I've shown you, this is quite difficult because as soon as the information is inside consciousness, it will be followed by a whole series of processing stages. So how do we do this? Is the decoded information used by the brain itself? We as scientists can decode information from brain activity patterns, but is that the same information which is being used by the brain? We need to interfere with the information. We need causal methods in order to interfere with the information and see that the pattern of brain activation and information processing changes. Otherwise, all that I've shown you today is correlational, and it could be that we decode better than the brain itself. And my third point, given that these decoding methods give us a very nice window on brain activity, is it possible also that this is a possible model of what some brain areas are doing? Is it possible that some brain areas are actually acting as decoders of other inputs from other brain areas? This is a very interesting line of research, trying to understand how, for instance, prefrontal cortex accesses the information for a given decision, sorts the wheat from the chaff, sorts the appropriate information for a given task, and therefore acts as a sort of decoder of activity in other brain areas. With this, I would like to conclude with the faces of the people who have done the work, Lionel Nakache and Jean-Rémy Sick for the work on the patients, and especially Jean-Rémy Sick for creating this idea of temporal generalization of decoding, which was published in TICS last year, Jacobo Sitt and Sébastien Marty did a lot of work, especially Sébastien Marty, on the PRP task. Jacobo worked also on the patients. And Moti Solti and Simo Monto did the masking study and the following of the spatial information in the brain, which I hope will soon be published. And a lot of this discussion about the global workspace model is in this book, which was published just a few months ago. Thank you very much for your attention.